Well, Professor Clements with you again as we continue working through our way through our book. This material is related to the OpenStax Physics book. That's chapter 20, sections 1, 2, and 3. Current, Ohm's law, resistance, and resistivity are our topics for today. We're now leaving the realm of electrostatics. Now we're going to discuss charge and motion in a wire and through electrical elements connected to those wires to see how we can start understanding electric circuits. Our basic definition when we have charge moving is current. Current is a measurement of the amount of charge that is moving in the wire, and amperes is the unit of the current. If we have 1 ampere, then we have 1 coulomb per second passing through a given cross-sectional area of the wire. So current is equal to 1 coulomb in 1 second traveling through the wire. And I hope you realize it's a tremendous number of electrons. The charge on 1 electron is 1.6 times 10 to the minus 19 coulombs. So you can do the reciprocal of that to find out how many electrons we need to get a coulomb, and huge numbers. So we're not going to draw all of those. We're just going to imagine we have some charge moving through here, and we'll discuss the implication of whether it's positive or negative charge moving just a little bit in this chapter, and more when we talk about magnetism. We'll talk about the determination of which sign of charge is moving in the wire. So we have a setup on, if we get the slides working here. Car battery creates a potential difference. Current is moving through the headlight, delivering energy to the wire there. It heats up and shines out. In a circuit diagram, a schematic diagram, a battery consists of a long line and a short line that are parallel to each other. The long line is called the positive terminal, and this squiggly line is a symbol for a resistor, a device that resists the easy flow of charge through the wire. Now you'll notice here this current leaves the positive terminal and heads towards the negative. It is actually the electrons in the wire that are moving, and they leave the negative terminal and head towards the positive. Well, so what's the deal with this slide? Is it a mistake, a typo? Well, if you go back into the library, if you have a library with some old books in the collection, you'll find that this current direction has been in place, has been the choice since the early 1800s. It's a traditional current. Again, Benjamin Franklin got us started here thinking that there was only one sign of charge, the positive charge, and for almost all purposes, it does not matter if it's positive charge or negative charge moving through a wire. Again, when we talk about the magnetism, we'll see a case where it does make a difference. And that's how experiments can be done to prove that it's the electrons moving through the wire. But we'll use the conventional current. We'll draw in the circuit, the current leaving the positive pole of the battery, going through electrical devices and coming to the negative pole of the battery, conventional current. Again, the charges here, there'll be an electric field established by that potential difference across the battery, and the plus charges would move in the direction of the electric field. The electrons that are actually moving, of course, move in the opposite direction. Force equals Q times E. When the Q's are negative, the force has the opposite direction compared to the direction of the electric field. But again, we're going to use conventional current. We won't worry about that. The wires here, you should realize that these are not empty cylinders. We have material filled in here. This is a solid material, and it's a little bit misrepresented on the drawings here, or you might be misled to think that the charges can freely move through this wire. They don't actually freely move through the wire. So let's go on to the next one. Here's a better representation of how the electron makes progress through the wire. And even this is a little bit misleading in that this distance is very short. Before the electron hits an atom, remember it's traveling through a solid, through the wire material, copper or aluminum or gold or whatever type of wire you have, steel, whatever the conductor is. The electron is moving through a solid. It's not completely filled in, there are gaps, but the electron is going to hit atoms and bounce off in random directions. The electric field applies a force on the electron off to the right, so gradually the electron does drift off to the right. And we have this drift velocity of the electrons in the wire, and it's a pretty small number. 1 times 10 to the minus 4 meters per second is typical drift velocity. So any one electron takes a long time to move through a realistic wire. But as this electron is coming in here, there's an electron out here that's moving through the resistor or the light bulb or the motor, whatever there happens to be in place. We don't have to wait for the electron that left the battery to reach the electrical device. So our devices work right away. We don't have to come in a few hours before we want to turn on a light and use it. We can have the light up right away. But we have this drift velocity. The electrons just gradually move through the wire from end to end. Then, considering a very basic law in circuits that have a battery and a resistor. So here's our battery. We take these wires to have zero resistance, no impediment to the electrons moving. That's not actually the case, but close enough. And we'll concentrate all the resistance to electrical movement in this squiggly line called the resistor. And it is true in these simple circuits that the amount of current in amperes represented by I, will equal the potential difference of our battery, the V, volts, divided by the resistance of the circuit. This resistance is measured in ohms, 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 and has an omega symbol for its representation. If you look at it, if I can draw an omega here, it's kind of an omega, but that would be our unit that you'd look for doing this calculation. Volts divided by ohms give us amps of current. If the resistance is higher, then it's harder for the electrons to go through here, and we get a lower current for a given voltage. If we use a battery that has more potential difference, there's going to be more push, if you want to say, on the electrons, and the current will be higher. In fact, this voltage over here, when this analysis was first done, this was called the electromotive force, and some batteries are still referred to that, the EMF, the electromotive force. It's not a force, it's a potential difference, and our slide here is correct to use the V symbol for voltage. If we rearrange this a little bit, we'd have V equals I times R, Ohm's law, V equals I times R, and if I draw it out here, the potential difference across any one circuit element is equal to the current in that element multiplied by the resistance of that element. V equals I times R. And if the voltage is higher, potential difference is higher, the current will be higher. This R is a constant of proportionality to, V is proportional to I. So we have this constant of proportionality. V equals I times R. Voltage across this resistor, if I want to find that, I can calculate it. If I know the current in this resistor, and I multiply by the resistance value, that will tell me the voltage from end to end on this resistor. So that's in section 2, where you should read about that and read a little bit more about some of the details there. You can imagine a little bit water flowing through pipes and having restrictions in the pipes to limit the water current. It's a little bit of an analogy to this. And there's a simulation at the FET site that you might want to do on Ohm's law. But let's go on to our next little unit here and talk about the measurement of voltage across the resistor. There are meters that measure voltage. They're called voltmeters. They're always put in parallel with the device you want to measure. I would not put this voltmeter in series with the resistor. The voltmeter itself has a high resistance. So current coming through here, almost all the current will go through the resistor. A little bit of current will go through the voltmeter, a very little bit. The voltmeter will have a resistance itself in millions of ohms or more for modern voltmeters. But in this particular circuit, I times R turned out to be 18 volts. That's what this would be reading. And we call this the voltage drop across the resistor. If we have some voltage in the battery, if these wires are perfect, then this would be 18 volts on this battery symbol. And we go down to 0 volts across the resistor. There's been a voltage drop of 18 volts across the resistor. As we move through a resistor in the direction of current, of this conventional current, the voltage decreases. So we have a voltage drop in the situation. And then calculating the resistance of a wire or resistor. The resistance, again, is a geometrical effect, something like the capacitor. But we have a constant here, different constant, the resistivity. This is different for gold or silver, for iron or copper. It's a number you can look up in a book, the resistivity. You multiply by the length of the wire in meters, and you divide by the cross-sectional area of the wire in square meters. So does this formulation make sense to you? We have a resistivity. It describes a little bit on how easy or hard it is. Describes how hard it is for the electrons to get through the material. If we have a longer set of barriers here, of obstacles for the electron to work their way through, to drift through, so the resistance will be higher. If our resistors are longer, we get a higher resistance. If the cross-sectional area is large, if there's a lot of space for the electrons to move through, they'll move through more easily, and we have a decrease in the resistance if the area is larger. If we constrict this to a smaller cross-sectional area, it's harder for those electrons to move through that narrow area. They're bunching up and repelling each other more. It's harder for the electrons to get through. If the area is smaller, the resistance will be higher. So what type of wire do you think goes into a house from the utility pole? A large wire or a small wire? And the answer is a fairly large wire across here. So the area is large and the resistance of that wire is small. It does not prevent the current getting into the house. We want a wire from the utility pole with a small resistance so we can easily have a big current into the house, a couple hundred amps. Then the book has an equation that describes this resistivity. It turns out there is a temperature effect. As the temperature goes up, this resistivity gets larger. So there's a little correction factor for the temperature effect, again based on the different materials. But just as a rough approximation, if we would have an alpha of 3 times 10 to the minus 3 in metric units, 3 times 10 to the minus 3. And we want to consider how much temperature change is required to double this rho value. Now, the rho is equal to a fundamental intrinsic rho, a rho naught, then the parentheses 1 plus alpha times delta T. So if we want to double the resistivity, the 1 plus alpha delta T would have to value of 2. So write this down on your own scratch paper. 2 equals 1 plus alpha delta T. That means alpha delta t is equal to 1. And if the alpha is 3 times 10 to the minus 3, then we can find the delta t by taking 1 divided by 3 times 10 to the minus 3. So about 333 degrees Celsius would be the temperature increase that would double the resistivity. That's a pretty hefty increase in temperature, but it does occur in light bulbs, conventional light bulbs where the wire gets hot, and it's even higher than 333 degrees Celsius. But that's a description of how we calculate resistance. It's a geometrical effect. The resistivity number here, there's a table of that for different materials, and we have a temperature effect that comes into play as well. As the temperature gets higher, the resistivity becomes greater. So that's an introduction to circuits with resistances. Keep reading and asking questions.